Hello everybody. In this video we will be discussing some certain examples on molecular diffusion and equimolar counter diffusion. So first we take an example of molecular diffusion of helium in nitrogen. We find certain problems here where we can apply fundamentals of diffusion and counter diffusion, equimolar counter diffusion. Here as an example has been stated. What is that? A mixture of helium and nitrogen gas is contained in a pipe at 298 Kelvin and 1 atmosphere pressure. Now it is told total pressure which is constant throughout. At one end of pipe at point 1 we are having the partial pressure PA1 of helium 0.60 atmosphere, and at other end, which is at a distance 20 centimeter apart, is having a partial pressure close as 0.20 atmosphere. Now it has been asked to us that calculate the flux of helium at steady state if diffusivity of A into B of the helium nitrogen mixture is 0.687 into 10 to the power minus 4 meters square per second. So we use CSI and CGS unit. So we are given that total pressure P constant and our total concentration C is constant, where C can be written according to perfect gas law as that C. We are having a perfect gas law PV is equal to nRT, as we know for ideal gases. We are having now N by V is our C, which can also be written as concentration, which can also be written as P by RT from ideal gas law. Also, now our pressure P, total pressure P is constant throughout. Now we have been told that where N is kg mole of A plus B and B is the volume in meter cube, our N is kg mole of A plus B, that is helium plus nitrogen, and B is the volume in meter cube. B has the units of meter cube. Sorry, this cube. T is the temperature in Kelvin. R is the given value of 8314.3 meter cube Pascal divided by Pascal kg mole Kelvin, and so therefore in the for steady flux Jz is constant. Now also DAB for a gas is constant. So we can write, if we know the writing. Hello everybody. I'm writing the flux equation, that is Jz or J simply is equal to minus DAB dCA by dZ. Now if we for steady state flux J is constant, now DAB for a gas is constant, we can rearrange, and on rearranging and integrating the above equation, that is equation number 1 equation. So when we integrate this equation, what we are going to get, we are getting some term like J Z star like this, from Z1 to Z2 dZ is equal to minus DAB, diffusivity of A into B, concentration from CA1 to CA2 dCA. So we are having basically 2 points at point 1 and point 2. We are having different point 1 and 1 2. We are having different partial pressure of helium. That is at PA1 we are having gases is there, some reservoirs is there which is connected. So these are closed reservoir at point 1 and point 2. We are having partial pressure of 1 as 0.60 atmosphere, and at point 2, that is partial pressure of A at 2 is about our 0.40 atmosphere. Sorry, 0.20 atmosphere. Therefore, for a helium nitrogen mixture, we are getting this value. While we rearrange this equation, we find that our Jz is related as, when we solve this above equation, that is equation number 2, we are finding out that Jz star, that is our flux of A and helium in Z direction, which is obvious at equilibrium, is equal to DAB. We take negative sign inside, that we are getting CA1 minus CA2, Z2 minus Z1. This is the difference in the path travel, or this distance. Z2 minus Z1 is given as our 20 centimeter or 0.2 meter. So this distance is there. Further, from perfect gas law, if we write from ideal gas law, perfect gas law, now we can write that PAV is equal to NA RT. Now, what we are getting is that CA1 is equal to PA1 divided by RT into NA by V. Now, while if we substitute all these terms in our earlier equation, that is this equation, and we replace the value from the instead of concentration for we write pressures in terms of pressure, we will get JZ star equal to DAV PA1 minus PA2 RT Z2 minus Z1. If we put all these values and substitute for the equation in SI units, we will get something of the form Z star is equal to 0.687 into 10 to the power minus 4. In SI units, we convert all these values 6.08 into 10 to the power 4 minus 2.027 into 10 to the power 4. Now after that, this is a simple mathematical calculation. Divided by 8314 into 298 temperature here and path distance of the car. Now if we solve this, we will find that Z star is equal to 5.63 into 10 to the power minus 6 kg mole A divided by second into meter square. Further, if pressures in atmosphere are given, we can also convert the same into CGS units and also the atmosphere. So for CGS units, we can also take in the value gram mole per second into centimeter square. Therefore, we find that other driving force besides concentration differences for diffusion also occur because of temperature, pressure, electrical potential, and other gradients. Now, this is the solution of our JZ star. Our value which was asked earlier, which is to calculate the flux of helium at steady state. So this is our answer. Now, in the next video, I will be discussing a problem on equimolar counter diffusion. Thank you very much.